Hello guys, this is Mr. Koi. This is just a quick little lesson on Newton's law of universal gravitation. So Newton was famous for discovering gravity, but really what he was famous for was the discovery that gravitation is universal, as in it applies to all objects. All objects attract each other with the force of gravitational attraction. Gravity is universal. Everything has gravity. The pen you're holding in your hand has gravity towards your hand. It's tiny, but he was able to develop an equation that would explain this and which also helped explain all the orbits of the solar system. So by definition, so this is a definition you should write. Definition. Newton's law of universal gravitation states that the force of gravitational attraction is directly dependent or directly proportional to the masses of the two objects and inversely or oppositely proportional. Oops, I realized I didn't spell it wrong. Proportional to the square of the distance between them. Distance between them. So that's wording. So let's quickly break that down. So what we can say is that the force of gravitational attraction is directly proportional. So that means that the force of, now we are using capital G, is directly proportional. That means, hey, as mass 1 goes up, right, this will also go up. And of both masses, so also as this mass goes up, this doubly goes up. And it's inversely, so the bigger the radius, or the distance between them is, and it's the square of it, the bigger this is. As this goes up, this will now go down. Let me color code those for you really quick. As this goes up, this will go up. As the mass goes up, the mass here also goes up. The farther away they are, that will cause the force to go down. So this is essentially the equation for it, but he found that there's a slight tweak to it. So if this is not equal, this is the proportionality sign. This little sign means proportional, or in this case, inversely proportional. But he actually found there's and actually not Newton, but someone about a century after him discovered that there's a constant that goes in here. They originally called that constant G, where G is equal to 6.67 times 10 to the negative 11 newtons times meters squared divided by kilograms squared. So yes, this is a nasty unit, but basically it's so all of these cancel out, which I'll show you in a minute after I show you the complete formula for it. Alright, so this is the full formula where the force of gravity is equal to the gravitational constant times m m1 times m2 divided by the radius squared. So you'll notice this is a capital G because this is similar but not equal to little g, which is Earth's gravitation. But this is related because all they did to find G was to move everything else over, because this is a constant, it doesn't change. The mass of the Earth is pretty constant, and how far we are from the center of the Earth is also very constant. So all they did is this huge thing is equal to G. So then it would become Fg is equal to our our mass, this mass, times whatever all of that equaled. So we can actually calculate it. So the gravitational constant was 6.673 times 10 to the negative third newtons meters squared divided by kilograms squared. Then multiply it by the mass of the Earth and divide it by the radius from the Earth. The mass is 5.972 times 10 to the 24th, so quite a large number. This is in kilograms. And the radius of the Earth is 6,378,100 meters about. So as far as the units go, this cancels, this cancels, this cancels one of them. Then, alright, so we have a lot of math to do really quickly. When you're doing scientific notations and you're multiplying these two things, this is equal to whatever these top things here add up to. So 24 minus 11 gives you 13, so whatever this is, it's 10 to the 13th. And I almost forgot, this is squared here. So if we do the top multiplication, we get 39.851 times 10 to the 13th over, and if you square that number, you get 4.068 times 10 to the 13th. Well, would you look at that? Those things cancel out. And then we just have to divide 39 by 4.06. And then you'll get 79.8. Look familiar? It should, because that's the one we use. It actually was a little off, it looks like, in some of my sig figs, so I got technically 9.796, which would round to 9.8. But anyway, and then your units on this is newtons divided by kilograms. A newton is a kilogram meter per second squared. If you take out that kilogram, you're left with meters per second squared, as in the acceleration of gravity on Earth. So hopefully that kind of showed where we got G from. And then we're going to do one practice problem with this formula. Alright, so with any physics problem, the first step is read the question. It's Mars has a mass of 6.39 times 10 to the 23rd kilograms. What is the acceleration on Mars? If your mass is 60 kilograms on Earth, what is your weight on Mars? So let's start with the first one. And also, if you remember back to when I said the mass of Earth, the mass of Earth is 10 times greater. So which one do you think has more gravity? Hopefully that will, hey, more mass equals more total gravity, which means, yes, your weight is definitely higher on Earth. And that's why Mars is quite close, which makes it a pretty decent planet to be on. Alright, so how could we solve this? Well, we want to figure out what the acceleration is. Well, you may not see acceleration in this problem, but hopefully you can go back and say, wait, F of anything equals the mass times the acceleration. Well, you have, well, maybe you don't know your mass, but that means you know, well, the mass of anything, the acceleration is equal to force divided by mass, which is exactly true on this. So you can do the same thing. So F gravity is equal to all of this extra stuff, but ultimately, if you get rid of one of the masses, as in what would your mass be, and divide it on both sides, this is now your acceleration. So acceleration is equal to capital G times the mass 1, which should be Mars, divided by the radius on Mars. Hopefully at this point in the question you're like, wait, Mr. Coy, but we don't know the radius. You're right. The radius on Mars is 3,397,000 meters. That's the radius on Mars. So this equation turns into the acceleration is equal to the gravitational constant, 6.67 times 10 to the negative 11 Newton meters squared, kilograms squared, times your mass of your object, which is Mars, 6.39 times 10 to the 23rd kilograms, over this large number squared. I'm going to erase some stuff to make room for you to just write it below. That these two 6's on top multiply to get about 42.6, and then times b 10 to the negative 11 times 10 to the 23rd, which means it's 23 minus 11, so these will cancel out. So it'll be 42.6 times 10 to the 12th over, which is equal to 1.15 4 times 10 to the 13th. So these don't quite cancel, but they mostly do. So we just have a times 10 on the bottom. So we essentially have 42.6 divided by 11. I'm basically just moving the decimal over. So 11.34, because I just multiplied that by 10, and this is equal to 3.76 meters per second squared. So that's the acceleration on Mars. So you'll notice it's about half of Earth. So you're basically twice as strong on Earth, you can think, or twice as strong on Mars, you can think of it that way. And then now that we know this, I can erase this math here and now solve for how much do you actually weigh. Because remember, your weight is just the force, gravity is your weight, and it's your mass times your acceleration on that particular gravity. So this is the gravity on Mars. And then now you just have to plug in. So your force of gravity on Mars is equal to your 60 kilograms times your acceleration, which should be 3.76 meters per second squared. Do the math and you get 225 newtons. That would be your answer. So hopefully from this you learned a little bit about gravitation. Sorry, it's another slightly longer video, and I will see you guys tomorrow.